Oh, I always love to get the excuse, yeah, but I'm going to be a medical doctor, so it's okay if I write messy. It's about to not be.
Yeah, I don't know about that actually.
So we were talking about the Hess cycle. Let's look at how. So let's do one more acid through the Hess cycle and show how these delta G's can tell us the strength of an acid. Because what we did, hydrochloric acid, okay. Hydrochloric acid and overall, or we were doing the enthalpies. That's a Hess cycle. So the enthalpy of the solution was what? 0.8 kilojoules per mole. Okay. Now let's look at hydroiodic acid. So, okay. Well, we'll go ahead and draw out the Hess cycle so we know what goes into to Hess's law. Okay, so this is going to dissociate. And the question is, how strongly does this acid dissociate? So that means we're going to go gas phase. Gas phase. Gas phase. And then the ionization. Oh, sorry. The ions will come next. So then the ionization phase. Well, we say ionization because they're both becoming ions. Technically, only one of those is ionization. Which one is the ionization side?
Which one's the ionization side? Is it the iodine?
Nope, it's the proton.
It's the proton.
So remember, ionization is stripping electrons away.
Oh.
So this is technically like the enthalpy of the electron affinity. So that's what that side is. I just say ionization in general because they're both becoming ions, but if we want to be exact for a moment.
So what do you call it with the iodine then? Just the
electron affinity. Over here, you're technically the enthalpy of your ionization energy.
I didn't know that. I feel like I was probably told that at some point.
Well, and that's the thing. That's one of the important things about these advanced classes when we recover things you've seen before, because it's been a few years.
Yeah, and now I have more context for it.
Yeah, yeah. And a lot of these topics, when you see them again, you're like, oh, I remember that. This is super easy. But the first time you saw it, it wasn't.
Yeah.
Yeah, and that's what you'll find. Because you'll finish here, you'll go on to a graduate school, and sometimes it can sound like the material you're going to learn sounds daunting, but the deeper the context you gain, the more you're going to look at systems and go, oh, never mind, I get it. I know what's going on.
I get it.
Like in quantum mechanics, the first time someone introduced to me the concept of spin orbit coupling, my mind exploded. Sure. I'm like, dude, I'm never going to get this. And now it's just kind of like second nature. You know, after a decade of working with it, like, oh, okay, I get it. You'll do the same thing. And then, of course, we go from the gas into the solution phase. Okay, so let's start taking a look at this. Okay, so our Hess's law. I have plenty of room. So what I'm going to do, I'll move this down so we can still see it. But I have like this weird symmetry thing where writing across that line bugs me. I miss chalkboards. It's because I got this beautiful chalk from Japan.
Mm.
And here people make like scratchy chalk that's all dusty. No, the Japanese, their chalk like writes like it's silk. It's amazing. Let's see. So we have our aqueous hydroiodic acid. We're going to turn that into hydrogen iodide gas. The delta H of this is going to be kilojoules per mole. Now the actual splitting and these here again, I mean, we do the best we can to get numbers for this, but like your hydrogen iodide, I mean, I guess you could talk about the bond strength. You could also talk about the enthalpy of breaking down the Coulombic forces. It's kind of hard to do that with a single molecule. So most of the time, what you're getting here is enthalpies, like your lattice energies. And so, like, since your lattice is going to be Coulombic attraction between a lot of these ions, it's just like how much energy does it take to break that down? So again, all this comes from experimental techniques where you're trying to figure out how do I actually model this? Okay, so we have hydrogen and iodine. This delta H is going to be about 295 kilojoules per mole. And then we're going to ionize the hydrogen. So this is technically, again, the ionization energy. So that's going to be, we're going to inject 1312 kilojoules per mole. And then we're going to work with iodine's electron affinity. This one is going to release energy. And then we're going to take our gas phase ions and put them into solution. Same with the iodine. And in Gen Chem, people thought Hess's law with like 2 equations was hard. All right. And so this is what we're going to add together. So when you add the left side, you end up with the acid dissociation. And when you add the right side, you're going to get about negative 0.7. kilojoules per mole. So still a strong acid, which means the dissociation is essentially zero, which we would expect for a strong acid. But if we actually look and we compare the hydrochloric acid at a positive 0.8 kilojoules per mole and the hydroiodic acid at a negative 0.7 kilojoules per mole, you can see that the hydroiodic acid is more favorable for actually releasing its protons. The thermodynamics of this tell us that hydroiodic should be a stronger acid. So you can actually use this to start approximating the strength of acids. Let's see, what's next? All right. Okay, so we're not quite there yet, but so what other things can you use to try to predict the strengths of acids? So we already talked about Ka and pKa, but we remember, for example, that for a solution, standard Gibbs energy is going to look like that. And so what we can do is we can end up solving for the Ka. So what are we going to do? Well, let's go ahead and we'll take the element of Ka is going to be the negative delta G over RT. Ka is then going to be so we can get this equation that we can plug things into. Now we see our gas constant. So let's say we have a T 298.15 Kelvin and R. When you're dealing with thermodynamic quantities, you know they're going to be in like joules or kilojoules. So you have to use the 8.314 because that's going to be in joules per mole times Kelvin. So you have to use the R that brings energy in. Okay, so now let's say, for example, let's try to judge the strength of HCl and hydroiodic acid using this method. Okay, so we know negative 35 kilojoules per mole for the free energy. All right, well, that means our Ka so I'm going to change that to joules. .314 times 298.15. This is going to give us a Ka. Now, just by itself, a Ka on the order of 10 to the sixth, I mean, that's a really strong acid. But as most papers and things you read, you will like to look at the pKa of the system. So if I take the negative log of the Ka, I get a negative 6.13 for hydrochloric acid. Let's do the same thing for hydroiodic acid. Okay, well, let me start with delta G. The delta G is going to be a negative 54.1 kilojoules per mole. All right, so again, our Ka is going to be E 54,100 joules per mole. That's still all right. the Ka you calculate here is going to be 3.01 times 10 to the ninth, and the pKa okay, so once again, so when we use the Hess cycle, we notice enthalpies of dissociation that show that hydroiodic acid actually crosses into the slightly negative enthalpies, which means that it's going to more readily give up its protons. Here, when we look at the pKa's, we notice the pKa of hydrochloric acid. I mean, it's still really negative, so it's very strong, but it's not as negative as the pKa for hydroiodic acid. Hydroiodic acid is very definitely the stronger acid. So we can use these nice little techniques to try and figure out, well, what's going on. Now, trends within within a series of oxoacids, and this is a whole section that I was able to reduce to one slide because you really only need to know this. So sometimes you run into these problems, like your oxoacids. Experimentally, there's really no good thermodynamic treatment, but we can still estimate the pKa values using what's called Bell's rule. So again, and here's the we're always waiting for for people to do this. Everyone always wants to go into research in grad school and some kind of new technology. They want to make the next CRISPR or something. But eventually we're going to need people to do this basic work and go, can I spend my career figuring out the thermodynamic data for oxoacids? It's because it's stuff we don't have.
Yeah.
That could open up a lot of doors. Like,
it'd be nice if there's like an easy.
Yeah, at some point, someone's going to have to go back and do some of this core knowledge work. But maybe someday we'll see. But what we can say is your Bell's rule is going to be, let's see, 8 minus 5n. Okay, and so, well, you see where your n comes in. So your generalized formula is going to be your EO sub n, OH sub n. And so you take your nitric acid here, your E is going to be your central atom, so your nitrogen. And then you notice that you're going to have, and you kind of need to know the structure of the acid. Because this, for your nitric acid, you'll have, 2 O's by themselves and then an OH. And so, of course, we saw that for that hydrogen to be acidic in an oxoacid, it has to be on one of the oxygens. So we're naturally going to get 2 O's and an OH. So you can estimate the pKa of nitric acid at about -2 using Bell's rule. Now take a second and see if you can tell me HClO2. What would you estimate the pKa of that one to be?
Okay.
So write out its formula in the generalized format.
Is it estimated to be 3?
It is, as usual. I didn't expect you to get it that fast, but all right. Let's just make it harder for me to keep up with material because you absorb things like a frickin' sponge. But okay.
I think so.
Okay. So what you got here is you have, well, you have to have an OH because it's an oxoacid. The hydrogen has to be on one of the oxygens. So your chlorine is your E, and then you're going to have a single O and an OH. And so since you technically have a value of 1 down here, your pKa will be about 8 minus 5 times 1, or 3. So again, and you know that HClO2 is a weak acid. And so this trend and Bell's rule can be very, very helpful in actually trying to estimate the strength of the oxoacids that you're working with. Okay, aquated cations. This is a nice section because it actually starts to introduce you to coordination chemistry a little bit earlier. Because like, look at that aluminum ion in solution. So you're gonna start learning about things called coordination spheres, coordination environments. So if you were looking at that and you were looking at the coordination sphere, which is the ligands coming in to interact with the central atom, what is the coordination? What would you say the coordination number of that environment is?
Like 6 or something?
It's 6, yeah.
Okay.
So it's just a different way to look at things and to think about it. Like what kind of energetic interactions are you getting around a central atom? That's going to be your coordination environment.
Okay. Oh, we're in Lewis space.
Yep.
Now.
Just kind of wanted to bring back what Lewis acids and bases were. Now, one thing to keep in mind is a lot of these cations are going to form octahedral environments, but that will start to change based off what's in solution and the size of the cation. So the bigger the cation, then the coordination environment will start to change. So let's see, what you're seeing here is you're seeing, so remember your intermolecular forces, your aluminum and your waters are forming an ion dipole interaction. That's going to form a coordination environment. You technically get electrostatic bonding.
What's the last bullet point talking about?
Oh, so that's talking about the rotation of the oxygen of the water molecule. So what it's saying is you're not just necessarily interacting with a negative region. Experiment shows that these water molecules are going to reorient themselves so that your positive charge density is going to line up with lone pair electrons. And so, yeah, you can't just have the waters coming straight in. You have to see these in a way where they're going to be lining up lone pair wise, because then again, it starts to affect the environment inside the solution. It definitely affects the symmetry of, if you could call these molecules, so stuff like that. And now we'll start deciphering nodes that are like lethal. Okay.
All right.
So aquated cations is Bronsted acids. So we remind ourselves, oh, Bronsted acids are proton donors. So we have Lewis acids and bases. Bronsted are acids are proton donors. Their bases are proton acceptors. Whereas Lewis acids deal with electron exchange. And so you see like one by one. So first you see a single deprotonation and then a second deprotonation. Why did it stop at the second deprotonation?
Probably not thermodynamically favored anymore or something.
It's not, but look at it. Why do you think that is? What happens to the ion after the second deprotonation?
Oh, it's even now.
Yeah, it's neutral. So it's going to stop there.
Okay.
Let's see. So if we go back to our aluminum here, gave you pretty much, so broke this down into like a general molecular formula. So if you're thinking about the number of deprotonations, you're really going to be looking at, so like your first one there. So your first one, you have some charge of positive N. You release one proton. That N is going to go down by 1. You're going to get a hydroxide, so on and so forth, until the point where you say like, okay, well, if I have an overall positive charge of K, then I'm going to need K water molecules, and then I'll end up with a neutral atom of 6 minus K. So your water starts out at that octahedral environment. I will gain K hydroxides, and then I'll end up with K hydroniums. So that's going to be the end of the overall process. Let's see. What was I trying to predict here? Oh yeah, trying to explain why some of these are stronger acids than others. You can look at different things that make some of it not make a. This is really where you're going to have to use some chemical intuition. So again, your strength of your acid is going to be due to the polarization of the OH bonds. How much does that central atom polarize the OH bonds? You can look at the cation charge density. So for example, let's say you have a really tiny cation, its charge density will be higher, which means it's going to polarize the OH bonds on the water more.
Yeah.
And when you say tiny, we're talking about like the actual radius of the ion. And so if we go down, we see that our aluminum cation, and we have aluminum versus titanium. And you notice how the pKa of the aluminum one is 5 and titanium is 3.9. So the titanium one is stronger.
Because of the size of
Not necessarily, because let's see, the radius of the aluminum ion is 53.5 picometers. The radius of the titanium 3 ion is 67 picometers. The titanium is larger.
Okay.
So we get something counterintuitive here. We'll work through these numbers and we'll see if you can tell me what's going on. So a number of things we can look at. We can look at the radius of the ion. We can look at how the water is interacting with the ion. We can also talk about electron shielding. So say around that central, like the aluminum or the titanium, if we think about electron shielding, does that play an effect? You know, how much of that positive core are those electrons seeing? And is that going to contribute to polarization of the OH bond? Well, sometimes it will. Sometimes it's not quite as intuitive. Okay, so let's take a look at the aluminum. And this is where people start to go, oh crap, the transition metals. Because they are going to do weird quantum mechanical and electrostatic things. Okay, so your aluminum 3 has a radius of about 53.5 picometers. Okay, so that's first off, that's something we can compare. In a lot of acids, the size of that radius is so that's going to be a higher charge density on the aluminum. That would suggest more polarization of the OH bond, but we've already seen the pKa's. Okay. Now, okay, so aluminum, the aluminum 3 plus takes on just the neon, so the noble gas core. Okay, well that starts to make sense then, because that noble gas core is very, very shielding. We can actually calculate the shielding and the effective nuclear charge. But there's something that is not going to allow, and I want to see if you can figure out the difference between the two. Okay, so the aluminum and the water, they're going to have this electrostatic interaction. And then let's think about I was supposed to do that down here. Oops. What was I supposed to write up here? Why did I give myself that space? Apparently, I don't know why I gave myself that space. Oh, no, wait. Because down here, I wanted you to compare magnesium. Okay. So let's say, so let's look at this neon. That is going to be Okay, so let's take one of those electrons in the 2p shell, okay? Now, for aluminum, Z is going to be 13. Okay, so we're looking for Z effective is Z minus S. We have to figure out S. Okay, so if I take one of those electrons in the 2p shell and say, how much is it shielded? Which is essentially the kind of the shielding you're going to be getting from electrons coming in. Or the shielding that electrons coming in will see, like the electrons on the oxygens. Okay, so in the 2s2p shell, we're going to have a total of 7 other electrons. Okay, I'm taking off one of the p electrons and saying how much shielding does it have? That leaves 7 electrons in the n equals 2 shell. You remember doing this?
I do remember doing this.
Yeah, it's a little review. So for all of the electrons in that shell, it's going to be 7 times 0.35. That's going to give us a shielding of 2.45. Then we have 2 electrons in the n-1 level. So the n-1 level is 0.85. That's going to give us 1.7. S is going to end up being 4.15. Okay. So that means your Z effective is going to be 13 or minus 4.15. And that is going to equal 8.85. So technically, any electron coming in is going to see about 8.85 of those protons in the core. Okay. Now let's think about that for titanium. Okay, so you see your titanium there. Where's your radius? Okay. Titanium is going to have a radius of about 67 picometers. Okay, so already we're saying, well, that aluminum should make a stronger acid. So this fails on the radius part. Great. Okay. Let's think about the ion structure here. So your titanium is going to be, at first, it's argon, and then it's 4s2,3d2. Okay. Titanium 3, argon core, 3d1. Okay, so we don't have the noble gas configuration for titanium. We have 1 electron in a wide open D shell or D subshell. That could make a difference. Let's look at for titanium. Z is 22. Okay, so if we think about the shielding of that 1 electron in the D shell, okay. So for this one, we would have to look for electrons in there is no 3F, so that's automatically out, but there's no more electrons in the 3D shell, so there's no shielding from that at the n equals 3 level. The 3D3F level. Those are going to be slightly higher in energy than your 3S, 3P. So what we know now is electrons in smaller shells are all going to contribute 1. So that means if I look and I say, well, I have that 1 in the 3D shell, how many electrons am I going to have in smaller and lower shells? The argon will give you about 18 electrons. Okay, so for electrons in other shells, you're going to have 18 times 1.0. And so that's going to be your S value, your shielding value of So it's going to be all of your electrons and your N-1, N-2, and then your 3s, 3p. Okay. So if you go back and review your Pauling rules for this, it helps make sense. But so now our Z effective for the titanium, 22 minus 18, which is going to give us 4.0. Well, the titanium shields incoming electrons more than the aluminum does, yet the pKa is smaller. So something's clearly breaking down between main group metals and transition metals. What do you think is happening here? What is the difference here that you think might be causing this higher polarization of the OH bond on the water for the titanium?
The titanium. Is it a larger difference in electronegativity or?
No.
Okay.
It's a different way that the electrons on the oxygens are interacting with the titanium. So how is the interaction over on the aluminum?
How is it?
Yeah, like how did the aluminum and the waters interact?
I mean, it's that kind of like halfway between covalent and like ionic, right?
Yeah, so you get that ion dipole interaction.
Yeah.
And you see the aluminum has that full, what will that full noble gas configuration not do that your wide open empty D shell subshell will do?
Oh, hybridize? No, I mean the noble gas one's more happy. Like it doesn't.
Will it accept any more electrons?
No.
So your maximum interaction there is going to be electrostatic. What about over here?
It would like to give one away, right?
Not give one away.
It wants to fill the D orbital.
It does. And what's it going to do that with?
It's going to steal them from the oxygen.
From the oxygen, which is going to cause what kind of interaction?
That'll be dipoles.
Not dipoles. If this is technically what we would call it, well, that'll give it away. Two ways to say it's either dative or coordinate covalent.
Okay.
Which is a what? So the oxygen is going to bring in electrons. Those are going to plant in that empty D subshell, forming a what?
Like an ion?
An ion.
What?
Electrons coming in from the oxygen, empty D orbital, they thunk and they join.
Polar covalent?
It's a bond.
It's just a bond?
It's a bond.
They're just having a normal, okay.
Yeah, it's a covalent bond.
Oh, okay.
So that's the difference here.
Huh.
So with the aluminum and your main group metals, you're only getting this electrostatic interaction because that noble gas configuration is not going to take any more electrons. Like you said, it's happy. This wide open D subshell is going to start accepting bonds from the water.
So transition metals can break the octet rule?
Oh yeah.
Oh, okay.
Oh, they're bizarre.
I thought you said that it was like that was a fake rule.
But
is that just for the?
Well, but that's the thing. I mean, they're going to have that resonance that we talked about earlier.
Mm-hmm.
You're going to have that ionic character coming around, but yeah, you're going to have that resonance, but they're still sharing electrons.
Okay.
And so those electrons shared from the oxygen, even if you're at a point where the water takes on a charge and the titanium takes on a charge, those electrons are still going to plant in that D subshell, and you're going to be getting this covalent character.
Okay, so if you wanted, it has more covalent character,
Mm-hmm.
but it still is doing that thing that we talked about.
Yeah, the resonance going around, not technically breaking the octet.
Okay, cool.
But yeah, in generalities, you can say that this becomes hypervalent, but it does that resonating effect that we talked about early on. But yeah, and it's solely that covalent character that causes a higher polarization of the hydrogens on the waters, because now this D subshell is really sucking electrons away. Yeah. And so you get a stronger acid. So it's a weird behavior. It's a weird behavior. And the deeper you go into transition metals, the weirder it's going to get.
Cool.
Okay. Now, here's one. I gave you two. Well, we've already done the aluminum. So I've given you two main group metals, magnesium and aluminum. Okay. Work on magnesium for a second, because what we remember for aluminum. Let's see if you can pull some of those shielding rules out of your head.
All right.
So for aluminum, your R is 53.5. Okay, now I'll tell you for aluminum, for magnesium, the R is 65 picometers, but you can't calculate that. Can you figure out now? In this one, you're not working with E or S. You're only working with the S and P.
Yeah, magnesium wants to be like argon, right? No,
Neon.
neon. Okay.
And Z is 12.
Okay.
Yeah, could you imagine doing this kind of analysis as a freshman?
Yeah,
I think you would have got it, but I think most people's heads would have melted.
I get it. I get it. It's,
You remember when your first year when I said we're just going to leave transition metals alone for a while?
yeah, I remember that. I understand.
The more you study them, the more bizarre they get. There are chemists who spend their whole lives just studying the transition metals because they pretty much have their own rules.
Does the okay neon goes up to 3p6, right? I don't know.
Neon goes up to a 2p6.
2p6. Oh my gosh.
Argon is your 3p6.
Argon is 3p6. Okay.
So remember, we're just going to be looking at one of the electrons from the 2p level. How much shielding does it experience? It gives us an estimate for other electrons coming in from the outside.
Yeah. I just couldn't find my Zeph rules. Like I couldn't remember what the things were.
Well, let's take a look at it and then kind of review those, because then we're going to have an exercise for this on Friday. So we'll start with that. Also, you're going to have another quiz this Friday.
Okay, cool. So it'll be 7 times, is that 0.35?
Yeah, so the rest of your, let's see. Yeah, so you're going to have 7 times 0.35, and then 2 times 0.85.
So it's like the same as the aluminum.
Yeah, so your S is going to be 4.15. The difference is your Z. So your Z effective, 12 minus 4.15. That's going to give you 7.85 as your effective nuclear charge. When we compare to aluminum, so first off, you see your aluminum up there is an effective Z effective of 8.85. Now you have 7.85, so the effective nuclear charge is less for the magnesium. your radius for the magnesium is greater, which leads to an overall effect of your aluminum cation is going to be more acidic. So you notice for your main group metals, these rules are they follow these nice rules. Always remember your transition metals are like the kids you played with on the playground that said, I don't care, I'll do what I want. You know, the ones who would make up rules on the spot. Like, dude, we've been playing this game for an hour. Yeah, well, new rule.
Yeah.
You know, that's the transition metals. Because you see all of these main group metals, they play by the rules. And you can actually predict the strength of the acid just by looking at nuclear shielding, ionic radius, stuff like that.
Cool.
So when we come back on Friday, we're going to work on this one, comparing aluminum to gallium.
Okay, I'll find my ZIF rule, so I'll be a little more prepared.
That was back in our first two chapters.
Yeah, that was a long time ago.
Now, if you go to forget, it's either chapter 1 or 2. There's a box in there that gives you like the list of rules. Also, on those slides, I wrote out the list of rules, so just kind of review them because a lot of stuff can really be judged by effective nuclear charge. Cool. Shielding plays a big role in chemical reactivity. Cool. All righty.